Welcome back to Probability and Statistics 1. This is Unit 2, Choosing at Random, Probability Models for Random Sampling. In this unit, we're going to talk about concepts like a random selection from a population, a random sample from that population, and we'll discuss the properties of those, the different types of random selections and samples we can do, and related concepts. So I'm actually going to break this unit up into two recorded lectures. The first one will deal with the basics and the concept of a simple random sample, and the next one will deal with sequential random samples. So let's begin with some terminology. Consider this random process. Choose a single card at random from a standard deck. So what do we mean by choose a card at random? Well, it means something specific in the sort of lingo of probability. When you say choose something at random, it means generally not just choose it according to some probability distribution, but rather choose it in the most random way possible. So when we're talking about choosing cards or a card from a standard deck of 52 cards, the most random way to do that would be to choose the card in such a way that all 52 of the cards were equally likely, right? Because if one card were more likely than others, then it would be easier to predict which card got chosen. So the way to make it most random, most unpredictable, is to make sure that all cards have the same probability of being chosen. So this would mean that we would have the probability model that had a sample space consisting of all 52 cards from a standard deck, and the probability of each outcome would be 1 out of 52. This idea can be generalized to the idea of a random selection of an individual from a population. So if we have a population consisting of n distinct objects, a random selection from that population is a random process such that first, each outcome is a single member of the population, and secondly, all members of the population have the same probability of occurring. So this phrase at random in a context like this means not only randomly, but in the most random way possible. And that turns out to mean in a way such that all outcomes are equally likely. Later on, we will consider processes in which, the probabilities aren't equally likely. So our first theorem here is pretty straightforward, just basically a summary of what we've already said, generalized to the case when we have a population of size n. A random selection from a population of size n is going to be a random process with a sample space that is equal to the population, and each outcome will occur with the same probability, which would have to be 1 over n, right? Because the probability of the whole sample space has to be 1. The one thing that I would point out here, and the theorem points out, is that if this is the case, then the probability of any event in the sample space is just the cardinality of that event divided by the cardinality of the sample space, because the probability of that event would just be the number of outcomes in that event, right, times the probability of any outcome, which is 1 over n. So that would be cardinality of E times 1 over n, but n is the same as the cardinality of S, so it's the cardinality of E times 1 over cardinality of S, or cardinality of E over S. So here's an example. Choose a card at random from a standard deck. What's the probability that it's a face card? Again, S would be the sample space consisting of all cards in a standard deck. It has cardinality 52. Our event E would be the event that the chosen card is a face card. The cardinality of E is 12, right? Because there's a jack, king, and queen in every of the 4 suits. So you would have 3 times 4 or 12 face cards in a deck. So the probability of choosing a face card would be 12 over 52, and that turns out to be about 23.1%. So that's pretty straightforward. Although the ideas here are simple, the problems can get actually complicated fairly quickly. I've got a set of discussion questions here that we'll talk about in detail in class, but let me just throw them at you right now and as sort of grist for the meal. The first one says, choose an integer x at random from 1 to n. Let a be any fixed positive integer. What's the probability that x is divisible by a? So, think about that a little bit. You might want to think about what's my sample space, S, what's the probability of each outcome in the sample space, and then think about what's my event, E here, what's its cardinality, and then you can arrive at the probability there. You might want to think about specific cases if the general capital N here is giving you a problem. You might think, well, just do a quick example, like pick an integer from 1 to 20. What's the probability that it's divisible by 3? Work that one out and then see if you can do it in the general case. Looking at the second question, it's kind of similar, but different. Choose an integer x at random from 1 to 1,000. What's the probability that x is divisible by either 6 or 8 or both? So here, I want you to think about that phrase, being divisible by either 6 or 8 or both, in terms of events. What kind of event are we talking about here? And then once you think about that, you can begin to sort of crack the egg into this question. It's not a trivial question. This one's going to take some thought. The third one is much along the lines of the second one. I think once you can solve the second one, you'll be able to solve the third one. Choose an integer at random from 1 to 1,000. What's the probability that it's divisible by at least one of 6, 8, or 10? So again, we'll talk about those more in class, but you might want to give those some thought now so you'll have some place to start from. So here's another random process. Choose a pair of cards at random and without replacement from a standard deck. So what do we mean by choosing a pair at random here? That would mean that every pair of cards now is chosen in the most random way. That is, every pair of cards is equally likely to be chosen. When we say a pair, too, in this context, we mean when we're thinking about, I have a card hand, generally the order that the pair is chosen doesn't matter. So let's assume that is the case right here. What do we mean by without replacement? Well, that simply means you can't pick the same card twice. So you're going to get a sample or a pair of two different cards. You can't have, say, the ace of spades and the ace of spades is not your pair. It has to be two different cards. That's what we mean by without replacement. The generalization of this would be the idea of picking a pair or a triple or, in general, a finite number of objects from a finite population. So consider a set of capital N distinct objects called the population. A simple random sample, or SRS, of little n objects from this population is a random process such that, first, each outcome is a subset of size n of the population, and second, all subsets of size n have the same probability. So simple random sampling, which you may remember from basic statistics, is equivalent to choosing at random and without replacement. Note also that if little n equals 1 here, we're choosing an individual at random, and that's just a random selection from the population. So a random selection means choosing an individual. A random sample encompasses that, but generally we're usually talking about more than just choosing an individual. We're talking about choosing a sample of a size 2 or more. Choosing a pair at random would be 2, and again, you can in general, you can have a random sample of size little n out of a population of size big N for any little n that's less than or equal to capital N, right? So what's the sample space for a simple random sample of size little n from a population of size big N? Well, if you think about the population itself, let's denote that by W. W just stands for the whole, the population, right? Then the cardinality of W would be capital N. But the sample space is different than W, right? Because the sample space is the set of all subsets of size little n that are contained in W. And so that second bullet point there, you see that sample space written out mathematically. It's just the set of all subsets E of W such that the cardinality of E is equal to N. And because all outcomes are equally likely, we're going to be needing to understand what the cardinality of the sample space is, as well as the cardinality of events in the sample space. First, let's think about the sample space. The cardinality of the sample space would simply be the number of subsets of size n that you could pick in a set of size capital N. So what is that number? Well, here's a theorem that gives us the answer. The number of subsets of size n in a set of size capital N is given by capital N choose little n, that's that first symbol, or another notation for that is capital N choose n, it's the binomial coefficient notation, but ultimately it comes down to capital N factorial divided by n factorial times capital N minus n factorial. I've actually got a supplemental set of slides in which we derive this. So we'll relegate the proof of this theorem to that supplemental slide set. It's called, I think, How to Count. And it's not too hard to prove, but this is the result we need to use, and so let's just focus on it for right now. There's a couple of conventions involved in this as well. For the convention we're always going to use is that 0 factorial is 1. That just kind of makes a lot of these formulas work out nicely in all cases. And a second convention we're going to use is that capital N choose little n is equal to 0 if basically the numbers capital N and little n together don't make sense, right? Like if you're trying to choose -1, a subset of size -1 from a set of size 5, there's no ways to do that. So that makes sense that that would be 0. Another way that this would not make any sense is if you're trying to choose, for instance, a subset of size 6 from a set of size 5. That doesn't make sense. And our convention will be that binomial coefficient n choose little n is 0 in those cases. And then we can use that to describe the probability model for simple random sampling. That's our theorem 2.3 here. Consider an SRS of size little n from a population of size big N. Then, first, the sample space is the set of all subsets of size little n from the population. Secondly, each outcome, which is of course a subset of size n, occurs with probability 1 over capital N choose little n, and that's simply because all outcomes are equally likely and there are n choose little n outcomes. And then finally, as before, because outcomes are equally likely, if you have any subset of the sample space, the probability of that subset would just be the cardinality of that subset, right, divided by the cardinality of the sample space, which in our case is going to be, again, n choose little n. So we'll see this theorem in action right away. Example 2 says, choose 2 cards at random and without replacement from a standard deck. So essentially we have a simple random sample of size 2 from the deck. What's the probability that both are face cards? So we need the cardinality of the sample space. Well, the sample space is all possible pairs of cards now that can be chosen from a standard deck. So that would be 52 choose 2. And that turns out to be 1,326. 52 times 51 divided by 2. So any specific card, any specific pair of cards has probability 1 out of 1,326. How many pairs now are in our event? Our event is the event that both cards are face cards. So how many outcomes are in that? Well, there's 12 face cards in a deck, right? And we need to choose 2 of them to get any specific outcome. You need to choose 2 of those face cards out of the 12 possible face cards. So the numbers of ways of doing that are 12 choose 2. That's 12 times 11 over 2, which turns out to be 66. So the probability of getting a pair of face cards dealt in a deal of size 2, right, would be 66 over 1,326. That turns out to be just a little less than 5%. So I have some more discussion questions then. Again, we'll go over these in class, but let's just take a quick look. Suppose we choose a simple random sample of size 3 from a standard deck. So you could imagine being dealt a hand of 3 cards from a well-shuffled deck. That would be a simple random sample of size 3. What are the possible outcomes? In other words, describe the sample space. How many possible outcomes are there? That would be the cardinality of S, the cardinality of the sample space. What's the probability of any specific outcome, right? That would be 1 over the cardinality of the sample space. And what's the probability that the 3 selected cards are all number cards, i.e. not face cards? So you could do this problem very similarly to the way the previous example was done, except the numbers have just changed, right? The sample size now is 3, not 2, and we want those 3 cards in our event to be number cards, not face cards. A second question, similar but a little bit of a twist to it. Suppose you're dealt a 5-card hand randomly from a standard deck. So that means you got an SRS of size 5 from a standard deck. What's the probability that all the cards have a value of 5 or less? So they're all number cards and they all have a value of 5 or less. And remember, an ace is considered a number card here. Its value is 1. So think about those, and we'll talk about them in class. Let's think about some of the properties now of a simple random sample. We know what an SRS is, right? It's a subset of size little n chosen at random and without replacement from a population of size big N. So let's denote by capital X the particular subset that is chosen randomly in an SRS. So the way that I'm going to denote this, throughout the rest of the course, this kind of situation is I'll say X and then tilde SRS capital N little n. That just means that X is the simple random sample of size little n from a population of size big N. So X is what we call a random subset of size little n from the population, right? It was chosen randomly and it is a subset of size n, so it's a random subset. In a statistical context, X is just our random sample. What are some properties of that random sample? Well, theorem 2.4 gives us some. Let X be the random subset from an SRS of size little n from a population of size big N, and let A be any fixed but arbitrary subset of the population. So A is not random, right? A is some fixed subset. X is our random sample. The first bullet point addresses the question, what's the probability that this fixed subset is contained in our random sample, right? And it gives that probability as this ratio of binomial coefficients. In the bottom, you see n choose little n. That's just the cardinality of our sample space, right? And so this is the standard thing. The probability of any event in an SRS is the number of outcomes in that event divided by the cardinality of the sample space. And the cardinality of the sample space for an SRS of size little n from a population of size big N is just big N choose little n. So the top must be the number of random subset, the number of sets of size little n that contain this specific set big A. And I'll leave the details for class and maybe for some discussion, but it turns out that the number of subsets of size little n that contain some specific set A is capital N minus the cardinality of A choose little n minus the cardinality of A. And that would give us that ratio gives us the probability of that event. One thing to notice here is that the probability that our random sample contains some specific set, this A, only depends on the cardinality of A. It doesn't depend on anything further. And that's an important point we'll come back to after we discuss this theorem. Let's look at the second bullet point. The second bullet point addresses the probability of the event that our random sample is contained in some fixed subset A of the sample space. So this would be like, imagine you take a random sample of size 1,000 of, say, registered Virginia voters. Maybe A represents the set of all Democratic voters in Virginia. You're asking here, what's the probability that a random sample of size N consists of all Democratic voters? It's probably a very small probability, right? But you could calculate it, and this shows how to calculate it. It turns out that that probability is the cardinality of A, choose N, divided by that same denominator again, capital N, choose N. Again, we'll talk about the reasons for this in class, but let's think about these results and what they tell us about simple random samples. And I want to focus, first of all, on the first bullet point, the probability that a simple random sample X contains some fixed subset A of the sample space. We noted before that that probability only depends on the size of the set A. What this actually means is that a simple random sample has no systematic bias regarding subgroups of the population, right? In other words, all subgroups of size 1 have the same probability of being part of the sample. No individual is any more likely to be in the sample than any other individual. But not only that, all subgroups of size 2 have the same probability of being part of the sample. All subgroups of size 3 have the same probability of being part of the sample, and so on. So no matter what subgroup you're talking about, a simple random sample is fair in the sense that that subgroup has the same probability of being contained in the sample as any other subgroup of the same size. And this is why simple random samples are sort of the gold standard for statistical sampling. They avoid any systematic bias in choosing subgroups from the population. And so on average, they're going to be representative samples. As an exercise, you can think about this probability. Again, A and X mean the same thing they did in our previous theorem. So X is a simple random sample from a population of size capital N. A is some fixed set in that population. What's the probability that A and X are disjoint? So think about that, and once we have a little more classroom discussion, I bet you can find the probability of that event, and then think about what that means in terms of the systematic bias or lack thereof of a simple random sample. Okay, so I think that'll be enough for right now. Again, we've got a few more things to talk about. In particular, we want to talk about sequential random sampling, where order matters. But I think we'll save that for a separate lecture. In the meantime, have fun with those discussion questions. We'll be talking about them in class, and we'll be back at you shortly in another set of slides very soon. Take care.